Hi, welcome to Module 3, Unsupervised Learning for Quantum Dots. So, everything we did so far was a supervised learning in a sense that we had the labels. Labels being, this is Star Wars, this is Star Trek character, or this is 1 dot, 2 dots, this is this line of, this is this type of charge transition, this is that type of charge transition. We, a human or a machine, always label the data. So we were training with respect to how far we are from a correct answer. The question is what to do if you don't know the correct answer, and that's what we are going to address today in Module 3. We are going to motivate a bit more why unsupervised learning, what it is, what are the reasons to use it and why you should. Then we look at how to analyze charge stability diagrams with something called clustering. In the next section, we also look at the charge stability diagrams analysis, but this time with the neural network, the so-called generative models that sort of supervise themselves, roughly speaking. And we are going to wrap up with a coding demo that Winnie is going to do for you, where again, you are going to test all the concepts hands-on in your own PyTorch code. So, let's move on to the first part, and that's the motivation for unsupervised learning for quantum dot data. As we said before, if we have labels, everything is super straightforward. We know the correct answer, so our loss function can be just predicted minus correct squared. We minimize that difference, we train the weights and biases of neural network. However, having a labeled data is not always available. In this course so far, it was available because there is a relatively simple theoretical model that lets you cheaply simulate a charge stability diagram. And if I simulate it, I know what the underlying parameters are, so I can just label it with a simple Python script. And this is what we did for you. In other instances, maybe the amount of data that you have is scalable enough that you can have yourself or your colleagues clicking in some graphic user interface and create a label sort of manually from the human expert experience. But there is a lot of learning tasks where either underlying simulation is not available or the data is too much that you simply cannot ask your whole lab sitting there several weeks and only labeling data. So the question is whether we can analyze quantum dot data without labels. In this module, we are going to illustrate it again on this simple charge stability data for a double quantum dots, but hopefully it will give you a foundational knowledge of how to generalize this to more complicated problems. We are going to illustrate this philosophy with two approaches. The first one will be the so-called clustering. This is something that existed in data science forever, and sort of informally it's part of a machine learning in a bigger picture sort of view, but really it's just a reorganization of your data, more or less. We are going to look at the simplest example possible, which is a principal component analysis, and then you are going to have a reading submodule to also see examples of a more complicated nonlinear clustering techniques. The second approach we will look at is with neural networks again, which by now we know and like, and it will be that of the so-called generative models, where we will use a neural network that will sort of supervise itself, and I will explain a little bit later exactly what we need by that. The specific architecture we are going to look at is the so-called autoencoder. So let's get started with the clustering first.